Okay. Hello, everyone. Thank you for attending. My name is Jeffrey Gillen. I'm a research data scientist and educator here at the University of Arizona in a group called Cyverse. And you have reached the third session, the final session of the workshop series Geospatial AI here at U of A in Tucson. And so today is going to be hopefully an end-to-end machine learning workflow to identify trees and aerial imagery. So that's pretty specific, but you can take what we learned today and apply it to the area of interest that you guys are interested in. This workflow is more like for the beginner. So if you're just trying to get into machine learning, deep learning, on imagery, this is for you. If you are a seasoned veteran, you might be bored to tears. So that's probably not for you. We're not going to go too deep in everything. We're going to go through an entire workflow, hopefully end to end, and have it work so you understand all the pieces. So you can basically get the gist of how the workflow goes. And then you can take that and then apply it to what you guys want to do. If it's aerial imagery for trees, great. If it's something else from imagery, great. Okay, let me share my screen again. All right, so we're going to go through a machine learning workflow. What are we going to do? Here are the basic stuff we're going to go through. We're going to start by getting a pre-trained model on Hugging Face. Hugging Face is I don't know, I guess you'd call it the GitHub of machine learning. If you don't know GitHub, I guess that analogy doesn't work, but it's a place, Hugging Face is a place where people share pre-trained models, they share data sets, other kind of like things that exist in the machine learning ecosystem. A lot of it is just kind of open, free to use. It's a very collaborative place. So that's where I often get my pre-trained models is at Hugging Face. Okay, we'll start there. We'll get a pre-trained model from Deep Forest. Then we're going to do some zero-shot prediction on imagery. So that means we're going to take the pre-baked model, run it on some of my drone imagery, and just see how it does. Right? And everything in this workflow is going to be Python. The whole thing is Python. It's all done in what's called a Jupyter notebook. And if you're not a Python person, that's okay. It's all been pre-written for you. We're just going to go through it and you're going to click the pre-written code snippets and it's going to run. So let's focus on what the code is doing, what the general workflow steps are, and let's not get bogged down into the syntax of the actual Python. We can just kind of skip past that and focus on what is it doing. Okay, so we'll do a zero-shot prediction on my drone imagery. Uh, it won't be so great. So then we will need to do some of our own labeling. We're going to go into a program called Label Studio. This part, I will show you Label Studio, but we're not going to actually go through the whole thing. It would take a little too long. So I have some pre-baked labels that I've already created that we can just all use, but I will show you what Label Studio is. Okay, and then sorry, I got to get this silly thing off of here. I can't actually see my screen. Okay, the third one is, so after our labels, we're going to take our pre-trained model and we're going to fine tune it. So we're going to train it on, our labels, our annotation, and hopefully that training like just tweaks the model a little bit so it's better suited to our specific task, our specific data set, right? Then we're going to rerun the prediction on our imagery with our new fine-tuned model, see if it does better. Hopefully it does. We will do a little bit of a assessment on the quality of this new model. Is it doing what we're saying it's doing? And then, yeah, that's pretty much the whole workflow. I've got some little other things of how to get data in and out, but for the most part, that's the general machine learning workflow we're going to do. It's all in Python. It's all in a Jupyter notebook. And along the way, feel free to raise your hand, shout out something, ask a question. This isn't going to be just a pure lecture. This is a technical demo, and things might go great or things might go off the rails. We never quite know when we're doing technical demos live. But yeah, you can stop me at any moment to ask a question. if you like. Okay. So what are we specifically doing today? We are going to be using a pre-trained model from Deep Forest. So Deep Forest is a Python library, and it's a pre-trained model. So some colleagues at University of Florida made this, and they were gracious enough to just put it out in the world on Hugging Face. It's free to use. So a pre-trained model is something that's already been trained to do something specific. In this case, it's been trained to specifically identify trees from uh, high resolution aerial imagery. That could be from an airplane, or that can be from a drone. So that's what it's trained to do. I can take that model and I can change it a little bit to then suit my exact task or my exact data set and hopefully make it better. So under the hood, this pre-trained model is a convolutional neural network, or a CNN. And the task that we are doing is object detection. So we're trying to find any tree in the image, and we want to put a bounding box around it. So that's the output, a bounding box, or object detection is our task. Okay, so let's talk about how this pre-trained model came to be. A couple weeks ago, I was talking about how machine learning models are like Legos and how someone can build something, then you could take what they build and build on top of it. All right, so let's track the lineage of the deep forest pre-trained model. So it all started with ImageNet. ImageNet is a data set, a large data set, several million images. It's one of the kind of foundation image data sets in machine learning. And it's not geospatial specific. It's not really aerial imagery. It's just everyday images of, a cow or a dog or a car or a person on a skateboard or something like that. And so these large data sets like ImageNet or COCO often are kind of the starting point for these machine learning models. Yeah, so start with ImageNet. And then somebody, I'm not sure who, they did a pre-trained model. They took all of those images in ImageNet, did some training to create something called a ResNet backbone. Okay, doesn't matter what that is at the moment, but that in itself is a pre-trained model. Okay, let's keep going. And so then my colleague at Florida then took that ResNet backbone, sorry, and he added his own training data. This ended up being 30 million trees that he extracted from the NEON Airborne Observatory platform. So NEON, National Ecological Observation Network, is a series of sites across the country, and it's all about long-term ecological research. And so part of that data set is they have an airplane that flies imagery, collects imagery at all these sites. And the imagery is 10 centimeters. And so pretty high resolution imagery from an airplane. Okay, and so my colleague at Florida was able to, I guess, using LiDAR and some kind of magic, extracted 30 million-ish trees from this NEON aerial imagery data set. Okay, great. He took all those and he trained it into the deep forest tree detection, detection for tree crowns. Okay, so he's made the pre-trained model called Deep Forest, which started with ImageNet, and then he added a bunch of his own data, all right, to get to where we are now, Deep Forest. So then I can take that and do what I want with it. And so I'm going to take a few labels. So it's about 100 or so. Maybe it's less than that, maybe 70, 80 labels of my own trees. All right. And this is from a drone. It's 2 centimeters. So it's higher resolution than the actual training of deep forest. So a little bit different, but quite similar. Okay. So this is what we're doing today. I'm getting my tree labels today, and I'm going to fine tune it, as we call it, to make Jeff's tree detector. All right, so that's what we're all going to do together using all the same data, and we'll see if it works. So yeah, the moral of the story, the take-home message is I don't need to go out and find millions of examples to make a good machine learning model. I usually can start with something that someone else has made, and many of those things that are made by other people are open, free to use on the internet, and Hugging Face is a great place to find them. Okay. So that's kind of the background of what we're doing. Let's get into the actual application. And so I did send out some emails, I think earlier in the week, describing what the setup was going to be. There wasn't really any setup except for if you wanted to get a Colab Pro account. So what is Colab? Colab is a Google product, right? And it is essentially a virtual machine on a Google computer, and it is running something called a Jupyter Notebook or a Jupyter Lab, right? Which is an environment to run Python. And so when we open something in Colab, that means we are connecting to a Google computer, and that Google computer probably has more resources than your little laptop. It's very easy to connect. Anyone with a Google account can do this. It could be a university account. It could be your own personal Gmail account. So Google is great at making things free, in a small tier. What's up? You can hear me, Carlos? Okay. So yeah, the only setup I suggested was to get a Colab Pro account. And if you're at a university, any university, I think you can get one for free. I just figured this out last week, and because I'm associated with University of Arizona, I just went through this little process here and proved that I am staff at the university, and they gave me a free free Colab Pro account, which essentially gives you a bit more computing resources. It gives you more memory, and it gives you access to more GPUs or better computing engines. You don't have to have the Pro account to follow along. There is a possibility you could run out of memory and it could crash. Yeah. So either way, we can all go through it together. And I'm just going to go ahead and open. So before we open Colab and get started, is there any kind of general questions? Essentially what we're doing today?
I had a quick question.
Sure, Ross.
Like for Jeff's tree detection model, do you have to train this for every flight that you do, or is it like can you train it once for a specific region and then you're kind of good to go from there? I'm just wondering like how I guess specific or like yeah, does that you understand what I'm trying to get at?
I think so. Yeah, models can be fitted well or overfitted, just like any model, right? And so if you know that your goal is to identify pine trees in South Carolina or something, then that's what I would train with. And this is easier than you think. We don't need, tons and tons of data. But you do have to give it data for the things that you want to find. If you're trying to find pine trees in South Carolina, but you're showing it pictures of mesquite trees in Arizona, it's probably not going to help too much. But yeah, that's when it becomes kind of an art of how much training data, what exact training data. Do you give it negative training data? There's really an art form to it that I probably don't have because I haven't spent years doing this. Basically know how the workflow goes, but I am not a deep machine learning engineer and know all the ins and outs of how to do this. Great. I'm more like like I said before, kind of like a tourist or someone that's just kind of hacking it together.
Awesome,
So yeah,
thank you.
it's going to take trial and error.
Hmm.
Carlos?
Yeah, I would like to add that in Jupyter Notebooks in Google Colab, once you have a training, you have finished training your model, then you can save like an executive binary code for that model, and then you can just reuse it every time. So you don't have to be retraining.
Okay. Carlos was saying you can, after you train them all, you can save it out and then reuse it. And yeah, we will go through that today. That's important. Once you do your training, you want to hold on to that thing. And so you can save it to Colab, you can download it to your computer, you can push it up to Hugging Face, if you want the world to access it, or you just push it up to Hugging Face just so you access it. It's really convenient to have all your machine learning stuff on the internet. It makes it easy, to organize your own stuff for yourself, but then also, hey friend, check out my model. Okay, any other quick questions before we open this up? Okay, let's get going. Okay, so this is where we're going to get into live demo time. And I hope it works. I've gone through this notebook several times, but you never quite know. Things can change. Okay, you guys can see it. So here we are in Google Colab. Right, we are on a Google computer virtual machine somewhere. I don't know where the computer is. But we are in what's called a it's called a Jupyter notebook. That's what this is here. And a Jupyter notebook is a great environment to interactively run Python. And so you can put Python code in these little code blocks here, like I've done, and then you could just hit run, and it will run the code. And so it's a great way for building code yourself, but then also sharing it and helping other people run code. And along the way, I'm usually providing comments and annotations. I'm talking about what I'm doing here. That's what all these pound signs and text here is, just information about the code you're about to run. Okay, so first thing we need to do in Google Colab is connect. All right, so I'm going to hit the connect button here. And if I click that, it'll show me what my resources are. Because I have a Colab Pro account, I have 50 gigabytes of RAM. I'm connected to a GPU, and I've got disk space also. We had a question in the chat. What did you post here, Carlos? How to save a Python file or model? Okay, thank you, Carlos. Carlos is providing color commentary in the comments. Thank you.
So what if we get, because I hadn't set up the co-op, but I could get it via pay, then I click on that, it says, I get the same thing on the right, but it says you're not subscribed, you currently have 0 computers available. But it also says, as at your current usage level, this runtime may last up to 4 hours, 30 minutes.
Okay, interesting. They change things all the time. Stephanie in here is saying that she's able to connect. She's not a Colab Pro subscriber, but is it saying you are connected?
Yeah. Yeah, I see the same thing.
How much RAM do you have? 12? Right here. Okay, yeah, so yep, yeah, I know. Yeah, okay, so yeah, for those who do not have a pro account, you'll still be able to click through part of it. But once we get into the heavier computation of the actual images, it might crash on you. You might run out of RAM. Okay, so let's just go ahead and get going. So we have our resources here. So I've got my little computer. All right, I have my virtual computer, and let's just start running Python. So the first thing I need to do is just install the Deep Forest Python library. So this Python library is in a repository called PyPy. So that's on the internet somewhere. And when I do pip install means I'm going to find the Python library from the repository PyPy, download it to my virtual machine here, and install it. Okay, so I think I did it. And so we're just going to go code block by code block and just hit play. So it should be simple for everyone to do. Hopefully it works for most people. Okay, so I've installed my Deep Forest library version 1.5.2. Great. Okay, a little bit of housekeeping here. I found that there is a library called albumentations that is not the correct version when you install Deep Forest. So this happens a lot. So I can uninstall the current version and then reinstall a earlier version. Okay, why Deep Forest documentation cannot be downloaded? I'm not sure. I'd have to go to that link to figure that out. Redirect notice. Yeah, okay. Yeah, when you leave Colab, it does a redirect thing. So yeah, here's Deep Forest documentation.
But you can read it online.
Yeah, yeah, it's not, you're not downloading it. You are just reading it online. Okay, let's keep going. I'm still in the process of getting set up. I'm installing the correct Python libraries and packages to do this work. So important thing that I should tell you is that, so when you install Deep Forest 1.5.2, it is installing a whole lot of other dependencies. So rarely when you install a package, does it just install one? Deep Forest is made up of a whole lot of other Python libraries that make up Deep Forest. And an important one is PyTorch. And so PyTorch is kind of the magic sauce in all of this neural network machine learning. It was originally developed by Facebook Research several years ago, but it's now part of the Linux Foundation. So it is an open source, completely free to use software, and it is basically the engine, the magic of AI. It is doing all the neural network prediction and training. And so when you get Deep Forest, you're actually getting PyTorch under the hood. Okay, and so also what you need to do in a Python notebook is then import the actual pieces of software that we're going to use. So you install, all right, that installs it on your machine. Then you need to import that software into our computing environment. So that's what these are here, these imports. Let's bring the specific software, into our environment that we need to use. Okie dokie. Now we're set up, and so now let's get something. Let's get our pre-trained model. So with this code snippet here, we are going to reach out to Hugging Face. Okay, like I mentioned, is the website where people post their machine learning models, data sets, things like that. I know exactly where it is. Here's the address. And Deep Forest Library has actually pre-written some code to do it automatically. And so I'll just click this button and it's going to reach out and get the pre-trained Deep Forest model for identifying trees in aerial imagery. Okay, we got it. It's been saved as model. So model is our pre-trained model from Deep Forest. Okay, then we got a little code to make sure we're using GPUs. So you click that, it should say devices CPU, and then it should say devices CUDA. So we are using NVIDIA GPUs. Curious, does it say what type we're using? T4. T4 is a type of GPU. How do we add Deep Forest documentation to Google Colab? I don't think that makes sense exactly. Deep Forest documentation is on a website created by the people of Deep Forest. It's not something you would bring into Colab. You can just have it on a different tab or something and reference it, if that's what you mean. Okay, so let's start predicting. So we have our model. We're going to do what's called zero-shot prediction now, which means I'm just going to take some random aerial images that I have. I'm going to run the pre-trained deep forest model on it, and we're going to see how well it puts bounding boxes around trees. So let's get these models. These are all on cloud storage in Cyverse. Cyverse is the place I work. We are cloud providers at the University of Arizona. We have a big cloud storage system. And so that's where I put random things. And that means you can get them. All right. So if you open this little folder tab, you can see here's the images I just downloaded. And am I able to look at one? Yeah, okay. So that's one I downloaded. Here's another one. These are all drone shots that I've collected over the years, I think. What else? Yeah, here we got Santa Rita, just for you, Cindy. Okay, so I've downloaded images from Cyverse onto my virtual machine. Great, blah, 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 blah. Okay, now let's try to do some prediction. Let's just try it on this one. Oh yeah, the prediction first spits out the results into an array or like a kind of like a grid. Let's actually do the image. Okay, so there's one of them. It kind of worked. I think it missed a lot of trees. Let's try a different one here. All I have to do is change the path of the image here, and it can predict on different ones. Okay. I mean, it is looks like it's finding some trees. Let's try image 3. Oh, there's my golf course one. Yeah, not bad. It is identifying some trees. Okay, so these are non-georeferenced images. These are just a single JPEG drone shot. All right, there's no coordinates. It's not something you can bring into a GIS. It's just an image, and we have identified trees in it. So it looks like it kind of works, right? We can tell that the model is doing what we want it to do, but maybe it's not so great. All right, so instead of just a single drone shot, let's now do it over a whole orthomosaic. So an orthomosaic is a product that you create from a bunch of drone images. So it's like I've taken hundreds of drone shots and I have stitched them together into one mosaic. And so this code block here is going to download that image into our Colab. So go ahead and click. It is a lot bigger. It's 735 megabytes. Right, and it's the size of it's like 10,000 by 26,000 pixels. So it is quite a bit bigger than the raw JPEGs we were doing, which were a lot smaller. They were 720 by 540 pixels. So much bigger image. But, we're here to do geospatial, so that's what we're probably going to be working with. So yeah, we have to up it. Okay, so in my folder here, I should now have something called Hole 17 Ortho UTM. That is my big ortho mosaic. So I've downloaded it to my Colab. Great. Now let's do some prediction. So that's what this code block is going to do here. We're actually going to take our pre-trained model. You see it right here, model, and we're going to predict tile. And so that brings up an important thing. Often in machine learning and large geospatial images, raster images, oftentimes you're not doing training or prediction on the whole thing at once. So often we'll take a large geospatial image and we'll break it up into what we call tiles or you could call it patches, or you could call it slices, or you could call it, I don't know, there's a bunch of different words for it, but it's taking an image and breaking it up into smaller squares. That makes it more bite size for the neural networks. It usually will reduce the amount of memory usage you have when you do training or prediction. So that's just a very common thing we do, is we are breaking it into smaller sizes. And so when we predict, we have something called patch size. And patch size is 600, so that means we're going to break our large image into smaller patches that are 600 by 600. And we're going to predict on those one by one. And then at the end, it combines them all again to see the full image. So let's just go ahead and do the prediction. And this is where the RAM, the memory use, is going to go up. And if you are not a pro subscriber, there is a chance you could run out of memory. Yeah. Yes. I was not able to get through this notebook last week without a pro account. But the pro account is free for a lot of people.
Oh, yeah, I used 12.4 out of 7 rounds.
Okay, you're already maxing out. Yeah.
Did you make this notebook or did you find it somewhere?
I built this from scratch. And I sure had a lot of help from Claude and ChatGPT to
Yeah.
help me with the exact syntax of the Python.
Yeah.
Right? And so that's what the large language models have allowed me and a lot of people to do, is I can think about the bigger picture of what I'm trying to do with Python and PyTorch and not be stuck in the weeds forever trying to write, 2 lines of code. Yeah, the LLMs, but still, he's your assistant. He's not just going to write the whole notebook for you and it's going to be perfect. That generally doesn't happen. I'm writing it snippet by snippet, block by block, and with a lot of effort. So putting this whole notebook together for sure did take effort. This was a couple weeks of work to do. But once you have it, you have a nice example, and then you can then build new ones that are sort of similar.
Yeah, totally.
Yeah, how are we doing here? Still predicting. Okay, I think we're about done with the prediction. My RAM has gone up. Okay. So that is using GPUs to do that faster, right? Graphical processing units. You could do all this without GPUs. It would just take much longer. GPUs greatly increase the speed of machine learning training and prediction. They do things in parallel as opposed to purely sequential or serial. And so, yeah, if you're doing machine learning AI stuff, a GPU is your good friend for making things just go faster. All right, so I've done my prediction and I'm going to plot it now. Let's take a look at what it looks like. Okie dokie. Okay, so here's my golf course orthomosaic, and all the yellow boxes supposedly are trees. I don't think I can zoom into it.
No fear.
Okay, let's close that. Is that what you mean? What if I...
On the read part,
What's that?
is that read part?
No, this is Paradise Valley Country Club up in Phoenix. Yeah, so I was lucky. I had a little job with them to drone map one of their holes. Hole 17 at Paradise Valley. Okay, so,
You can right click on it and save it out if you want to zoom in on it.
okay. Save as.
It's not good resolution, but you can still see it a little bit better.
All right, thank you. Yeah, thank you for that. Yeah, here we go. So every yellow box supposedly is a tree. Obviously, we have some commission errors. We are identifying things that are not trees. And a lot of times when there's one tree, it thinks there's like 6 of them. So it's doing what we think it's going to do, but just not very well. I'm not surprised. The deep forest pre-trained model was based on 10 centimeter aerial imagery, and this is like a centimeter and a half, something like that. So this is much higher resolution. So there's a mismatch in the trained model and then what I'm asking the pre-trained model to do. All right, so that means we need to make it better. All right, how's everyone doing so far?
I crashed.
Crash? Yeah, I figured some crashing might have occurred. Anyone else able to get through this and get to the point I'm at? Anybody?
Yeah, I'm there with you.
Okay, excellent. Do you have a pro account, Ross?
I do. Yep.
Oh, nice.
Thanks for that tip, by the way.
Yeah, I just found that out like a couple weeks ago, and I'm like, oh. Yeah, Google's just getting their hooks in deeper with me. I think that's their plan. They're like, let's just give them a little bit more. um, yeah, so Google Colab is great for teaching and doing these types of workshops. If you're doing your own production of this, you could use Colab as kind of an experimental thing. But if you really are doing this at a bigger scale, you're gonna have to pay Google a lot of money to use their hardware, or better yet, use your own. If you're able to do this locally and you have your own GPU, your own machine, and you're doing a lot of machine learning, you should probably do that. But yeah, Colab is great for teaching and just kind of beginner stuff. Okay, at least we have a few people that have gotten through it. Excellent. So our results using the pre-trained deep forest model is not great. It kind of works, but not fantastically. Let's make it better. And so we need to provide training data, our own training data. You could also call this labeling. And the program that I like to use is something called Label Studio. So Label Studio is something I have, and it's free to use. It's open source software, totally open source software. I've got it, here on my computer. We're not going to go too deep into it. I'll just kind of get you the basics of how this works. So if you're in Label Studio, you can create a project. We'll call it Deep Forest Golf. Okay, great. I'm going to put some data in it. What we got in the chat here? Oh, thank you, Carlos. Actually, before we do that, let me go back to Colab. Yeah, I forgot to mention an important thing. Okay, so we want to label images of trees to improve our model, right, for our golf course. You could do that, like traditionally in remote sensing, people would do this in a GIS. They do it in ArcPro or QGIS or something. So you're working in a geospatial coordinated environment. When you're doing machine learning like this, you do not need to do that. It's actually easier to take images and take them out of the geospatial world and just into image coordinates and do the training that way. And so I have a code block here that will actually take my big raster, that big in the orthomosaic of the golf course, and then split it up into smaller chips or tiles or patches or whatever you want to call it. And so it's going to split the raster into chips that are 1200 by 1200 pixels. Okay, let's just do that. Okay, so in my directory here, it's creating these new chips. It's making a bunch of them, so it's taking a little bit of time. Oh, interesting. Let's try another one. Keep getting the edges here. Okay, so yeah, here's a chip. So this was taken directly from my orthomosaic, and here's a 1200 by 1200 chip or tile, right? This is just a small, much smaller portion of the large orthomosaic. It's a PNG file, so that's just an image. It has no coordinates associated with it whatsoever in terms of geographic coordinates. And so that's what I've done here is I've just created a whole bunch of these little chips and output them. Oh, here we go. There's the lawnmower of the golf course. Right. And so we're going to do our training on these smaller chips, not on the full-blown orthomosaic.
So if we want to have the end result be georeferenced, is that still possible if you use this method?
Absolutely. Yes. And so we can do our training and yeah, we can do our labeling and our training in non-geospatial world. Right. But then when we actually, then we can actually predict on a geospatial image with that model. So yeah,
Got it.
I will keep going here. And I think it will kind of, yeah, reveal itself. So we've got a bunch of chips here. These are just PNG files, right? There's no coordinates, no geographic coordinates. And let's bring them down to our local machine. That's what this is going to do. It's going to download it. I believe, what's it going to do? It's zipping it. Okay, it's zipping it, and then it should be downloading it. Okay. So if you click that button, it's downloading something to your machine. It's downloading all these chips. I'm not sure how big it is. I'm sure it's several megabytes. I'm not sure how many megabytes. It created 198 chips. Great. Downloading to my local machine.
So all those files, like all these files that you're creating, that you're downloading, I guess, in your virtual environment, do
Yep.
those just disappear once the session ends?
Yeah,
You
good
don't
question,
download them
Ross.
locally?
Yeah, that's correct. So if you use Google Colab, you're connecting to a virtual machine at Google. And then once you disconnect, everything you've done here vanishes. It's just turned off and it's gone forever. So Colab is a great place to do work, save it out somewhere on your local machine, and then open it up later in Colab. Yeah, so things are not gonna persist in Colab.
Got it.
It's kind of how a lot of cloud stuff happens. A lot of, yeah, cloud
Mhm.
software. It's like you turn it on, you use it, you turn it off, it's gone.
So I think since I crashed with the previous step, I don't need to bother
You can pick it. I think you can pick it up a little bit later. Yep, we can go right. Yeah, I think if you restart your session, Stephanie, then you can pick it up. Yeah, we'll get there. Alrighty. Okay, so I downloaded this zip file here. All right, let's just extract it. And so I've got a folder with a whole bunch of chips. And if I look at one of those chips, yeah, that's what we created, and that's what we downloaded to our local machine. Now let's go back to Label Studio, which is software that is on my local machine. Right, so that's something you might not be able to follow along right now, but that's okay. Let me just basically show you how it works, and then later on, you guys can get the software and try it yourself. Okay, let's get a few of these chips. Great. Now I get to choose here, what type of labeling am I doing? And this is what's really cool, is that there's all different types of labeling for different types of tasks. We are interested in object detection with bounding boxes. So that's the type of labeling we're going to choose to do. But there could be segmentation for masks, semantic segmentation, key point labeling. There's even video in here, I believe. Yeah, there's like a lot of different kind of flavors or different tasks that you can specifically label. And the software is really set up to make it efficient. Yeah, if you look here on the left, here's all the different types of labeling you can do. It's not just images, could also be for natural language or audio. Yeah, video, time series analysis. So yeah, Label Studio is a great little piece of software. It's free to use and it's powerful. Okay, thank you, Nate. If you're on a Windows machine, okay. If you just do it, it won't. It needs the .zip file extension. Okay. Okay, so we are going to label. We're doing object detection with bounding boxes. Okay, so here's where I'm setting up how my labeling goes. I'm going to create something called tree. And we're going to delete airplane and car. That's just what they had there as kind of a default. I'm going to create something called tree. And importantly, though, it has to be capitalized because that's what Deep Forest wants. I did this whole workflow and I had tree not capitalized and it failed. So sometimes you have to get real specific in how things are done. So tree, capitalized tree, great. That's all I need in here. All right, save. And so then I can go to one of the images, and here's where I can actually do my labeling. So I'm going to go through as many images as I want and just start putting bounding boxes around them. Go to a different image. I got to click tree. Great, there's another one. Yeah, it starts to get hard. And you're like, how do I put bounding, how should I do the bounding boxes? So yeah, it becomes an art form of how to exactly do the bounding boxes, how to do the training. We could try it like this. That's one. Let's see. Let's think that's another one. So an important thing to really keep in mind here, I should put this like in bold print, is that when you're providing training for an object detection model like Deep Forest, you need to label all of the trees in this image. If I don't, and I leave trees unlabeled, it's going to assume that that is not a tree. And I believe I've said something like that in the comments. How did I say that? Yes, so when we use labeled data in the training process for object detection, we need to label all trees in the images. Object detection models use non-annotated areas in an image as a negative data. Okay, so if there's a tree in my image and I don't say that's a tree, it's going to assume that it is not a tree. And so that is also why we're doing things in these small chips. It is so much easier to label all of the trees in a little chip as opposed to the entire orthomosaic. Does that make sense to people? So in other words, don't provide the model bad information by giving it an image of a tree and not calling it a tree. Can you use polygons for labeling instead of boxes? In this case, everything is a box. So generally, object detection is a rectangle. If you want to get more specific and get like actually the actual outline of the thing you're looking for, that is segmentation. So that is a different type of task. It's very similar. Yeah, thank you, Carlos. Bounding boxes have 4 coordinates. It's that's the only way this will work in our object detection model is some kind of a rectangle. If you want to get the actual outline of the tree, you want to do something called semantics or probably instance segmentation. And that's just a different type of task. And you absolutely can do that. You cannot do that in Deep Forest, though. You'd have to find a different architecture that's specifically for segmentation. Okay. So yeah, so I made a few bounding boxes here. This thing, I mean the air conditioner sounding. It's this. I don't know. we've got some noise here at the library. Okay, so I'm gonna hit submit here. That means I'm apparently done labeling. Let's get into projects, and then I can export this. Okay, so when I export, this is where we export the images and then something called annotation. Annotation is just a text file that describes where every bounding box is and what its coordinates are. Okay, it's a simple like CSV file kind of looking file. And so when you export your labels, it has two parts. It has the images themselves, and then it has a text file saying bounding box 1, it occurs at these exact coordinates. And when I say coordinates, I mean image coordinates. So we're not in geographic space, we're in image space. And so I'm not sure, but maybe the top left is coordinate 0, 0, that kind of thing. So it's telling you where those boxes are exactly on the image, but image coordinates, not geographic coordinates. When you export your labels out of here, there's a lot of different formats. That's what all these things are. Cocoa format, Pascal, VOC, XML format, YOLO format. These are all essentially doing the same thing. It's just different machine learning models want the format to be a little different. Yeah, they are accomplishing the same thing. And so we export as something called Pascal VOC XML. That is simply the easiest way to get it into the format that Deep Forest wants. And so if you're using a different model, like if you're using Detecto, which is a different machine learning model, it wants something different. So every ML model has its own kind of specifications of like how it wants annotation and how big the patches should be. There's a lot of kind of details to dig into, but yeah, so we'll just export this out. I'm not going to actually do it. I've got something already pre-baked. And so that's all I want to do with Label Studio. It's a really powerful, quick way to do your training data in a non-geospatial environment. And so my next code snippets are actually downloading labels to our Colab environment here. So we'll go to this code block here. Okay, Stephanie, this is where you can pick back up, perhaps. Okay, multiple tree classification. Like we're looking at a forest image, but only want to look for a deciduous tree. Do we not label coniferous trees? Right. Thank you, Moritz, for the question. And Carlos, yeah, that is basically correct. If you're trying to identify just conifer trees and there's a bunch of non-conifer trees in your image, then yeah, you probably need to label. Well, if you're just trying to do coniferous trees, you could leave the rest of them as just empty space, and that should probably work too. Yeah, if there's a deciduous tree and you're like, no, we don't care about that, then just don't label it. Alternatively, you could do what Carlos says, which is you could have different labels for different types of trees. And so deep forest is meant to just identify a tree. Like it's not out of the box designed to identify different species, but of course you can train it to do that. If you would like to have a class called deciduous, a class called conifer, a class called whatever, you could do that with deep forest. Okay, so let's say we're done with Label Studio. We have our images and our annotation. We have new labels, and we're going to bring them back into our Colab environment. So I'm going to run this code snippet here. Okay, that's not what I want to do. That code snippet will make it so you can upload directly from your local computer. So I'll cancel. I don't want to do that one. I want to do the next one, which is download it from Cyverse. And so everyone connected here should be able to just click this, and it should download the labels, the annotations directly into Colab. Yeah, these are sitting in Cyverse data storage on the cloud. And we can just pull them down to our Google computer. And let's see, did we get them? Yep, we have a new folder here called labels. And that's exactly what we need. So yeah, let's see what we have here. Images, annotations. Thank you, Carlos. Okay, so here's the example of the annotations. Okay, yeah, so this is what we outputted out of Label Studio. I know this is not very human readable at the moment. It needs to be kind of organized better. But it's simply looking at, it's saying that there are like 4 or 5 labels, and here's the coordinates of those labels. And then it's saying what image is it, connected to. And so we have annotations and we have images. So those are our labels. All right, so then we have new information to train, or what we call fine tune a model. All right, we got to run this code snippet here. That's just to convert the annotations into yet another format that Deep Forest wants. That code snippet, what did that do? That created a CSV file. Let's see what that looks like.
Go on.
Can't? Did you run out of something? There could be a variable. Did you go and install the software again and import all the packages again? Yeah, that yeah. Yeah, you'd have to do the beginning stuff again, Stephanie. Yep. Okie dokie. Okay, we'll continue. So we've got our new training labels. We've got them into our computer, our Google computer here. And now, for good practice, we're going to split some of them into training and some of them into validation. If those that come from the remote sensing world, this makes total sense. We need independent data that is not going into our model to then validate how good our model is. And so I have got some Python code that's just going to split our annotations into, I believe, 75% is training and 25% is validation. Okay, that's all that did. Great. Okay, now we're getting close to the fun part, which is the training, which is the most computation. And so let's set up our training. What do we want to do here? We need to use a GPU. That's what that's about. That's not important. You can skip that. Okay, it's saying that we have training and we have validation. And this is the important stuff to look at. This is what we call parameters or hyperparameters. There's a lot of different ways, a lot of different details of how you can set up machine learning training. I wouldn't say I know the exact perfect way in this case, but you can choose epochs. Can you give me a definition of an epoch, Carlos? Do you have like a succinct? Yeah, it's an iteration through all the data. I know that's not a very satisfying definition, but yeah, these are all just different parameters that can be fine-tuned to really get the results you want. Batch size is how many of the chips do we push into the model at one time in the training. Again, that's kind of it's about saving memory, but there's a lot of different ways you could do it. We're just going to choose 16. Let's not worry about what that means exactly. The number of workers, we have 2. And then we have something called score threshold. And we will get down to what that means in a little bit. But yeah, let's not get bogged down in these parameters. That's more of a education and theory of machine learning, which I wouldn't say I'm the best person to help you with, honestly. All right, so I'm just going to hit play here, and this is going to set these parameters before the training, right? That should happen pretty instantly. And then I actually get to train the model. Okay, and if I click this, that means it's going to actually do the training. And it's going to use a lot of GPU resources. So I just want to look at the resources as we do the training. All right, I'll just go ahead and hit play here. Okay, so it's going to take a few minutes to do this. But we are taking our pre-trained deep forest model, we are applying our new labels to it, and we are changing, fine-tuning the pre-trained model based on this new data. And hopefully the new model is more aligned with what we are trying to accomplish. Okay, that was quick. Yeah, if you're doing this for real, you would probably provide more training data than I did. I did it very quickly. I think there's a total of like 75 images. I'm not sure how many total. No, there might have been 75 total labels. So it was pretty small training set. Anyway, it did run. So now we've created a new model. We've taken old model, we've made it new and improved, and now that model should do something different. Hopefully is better than what we saw before. All right, so I'm going to click this button here. We are now predicting. We're taking the new model and I'm using it to predict on my golf course orthomosaic. It should be using a bit of RAM, a bit of GPU. And how's everyone doing? Do we have any people that have gotten all the way to this step? You there yet, Ross?
Yep, so still hanging in there.
Okay, good. Yep, I made it. So all I have to do is click. I have to do click, run. But yeah, it will take some time afterward to be like, okay, hold on, what did all these steps do? That might take you some time, but just trying to get through the concept of the whole workflow. Okay, so we've taken a new model and we've now predicted onto our golf course orthomosaic. Let's take a look at it. How well did we do? Drum roll, please. Okay. That looks better. Let's look at them side by side. Okay, so the image on the left is our new fine-tuned model predicting on our golf course. And then the one on the right is the pre-baked, pre-trained model from Deep Forest out of the box. And yeah, you can tell there's definitely a difference on pretty minimal amount of labels. I barely did much. Maybe I made 75, 60 labels, something like that. It's not perfect, but it is, I think, definitely an improvement. What do you guys think?
Yeah, I think it's way better.
Yeah. So for let's see. Yeah, like this tree here, it thought there was like 12 trees. But when I trained it, it did a much better job. It's like, no, that whole thing is a tree. Yeah, so that's basically how this goes. Of course, if I want to make it really good, I'm gonna have to spend more time doing it. I'm gonna probably have to iterate through this several times. I probably have to get more training data. I might have to provide it negative data. And so that's another strategy. Instead of just not labeling something, you can actually label something and say that this is not a tree. And so you can provide it negative labeling, and perhaps that could help make the model better. And you'd also have to fiddle with the the hyperparameters, all the little different things, little different knobs you can to make this better or worse. And that just takes a little bit of effort. So yeah, so here's some errors. It thinks this sand trap bunker is a tree. It's definitely not a tree. So I would have to go in and maybe provide a negative label saying that this is not a tree, and hopefully it would teach it well enough. Okay, so we got the basics. And what do we have left? We got a little bit more housekeeping here. It's 11:09. Thanks for sticking with me, guys. All right. And so what else would you need to do here? So yeah, these Google computers, Google Colab, they self-destruct after you close them. And so we want to get our stuff out, right? Anything that you have here, you can just download if you want to do that. Upload. Is there not a download button? Oh, yes, there is. There. Download. So you can get data out that way. You can download here. You could through the terminal, if you are a bit savvy of how to use a Linux terminal, you could do it that way, or you could write a little Python to do it. Okay. What else? So let's get the bounding boxes out of here. And so that's something we might want to hold on to, or the actual boxes, the yellow boxes, and export them out of here. And we can export them as a GeoJSON, as a shape file. That's what I have written here. You could export it as any kind of vector format you want. You just have to write a little bit of custom code to do it. And so for me to do that, I actually have to run the prediction in a little bit different way before I can export it as a vector. So yeah, I hope you guys saw that. So we did our training or our labeling, we did our labeling in a non-geospatial environment. And then I did my training with that. But now that I have a model, the model itself is not inherently geospatial. It's just looking at image coordinates. But if you do it on top of a geospatial image, it will then do it in a geospatial way. And so we made our model, and then I did it, predicted on top of this geospatial orthomosaic. And now we have predictions that have actual coordinates, actual geographic coordinates. And so you're kind of moving back and forth between geographic space and image space. All right, if I click this button here, I will actually output all those vectors, all those bounding boxes as a shapefile and as a GeoJSON. Let's see, did it do that? Yeah, here it is. So tree box is GeoJSON, and then my shapefile consists of these 5 files here. So I can just download all of those if I want. Okay, and so that's a way to get the predictions out, get them out of Earth Engine, or sorry, out of Google Colab and down to your computer where you can do whatever you want with them. Then you could take those and bring them into QGIS or ArcGIS or whatever. They should have geospatial coordinates. I hope. I think. Yep, it is, should be. You look here, it is using geographic coordinates. So that should work. We bring that into a GIS. Okay, what else? So we've done our predictions. We've exported those predictions out. Another thing we could do is assess the quality of these predictions. to iterate, I usually just look at things with my eyeball. The human brain is pretty good at just looking at something. I mean, like, yeah, that looks better. That looks good. That looks terrible. But if you want quantitative data of like how good your predictions are, one way to do that is something called intersection over union. And we're doing that specifically for bounding boxes. What is intersection over union? So it's this equation right here. It's the area of the intersection of the ground truth and the predicted boxes divided by the area of the union of those two things. So it's the intersection divided by the union, and that's just a simple fraction of saying how good a prediction might be. It is kind of a simple way to do it, and people can definitely poke holes in its theory, but it is kind of it's kind of a simple way. Something called an intersection over union. You're just comparing the truth of the bounding box versus the prediction of a bounding box, and how well do those two boxes line up with each other. And we can do a simple ratio between the two to get a measure of accuracy.
You might not even have a detected box in some cases.
Exactly. Yeah. Stephanie said, like, what if there is no detected box? Right. And so then what does that get? Does that get you a 0 in that case? Or yeah, I don't know. I haven't thought that far ahead, honestly. There are other more sophisticated ways to do it. This is just kind of the simplest thing that I've come across for bounding boxes. If you need quantitative data for how good your predictions are.
I mean, I would be super happy if I got a box for every tree, even if it's like 50% off.
I know,
For me,
right?
It would be like percent set,
Yeah, but for sure you're gonna get a ground truth box that has no predicted box, or you're gonna get, or the opposite. It finds a box that's not really there in truth. Yeah. So what do you do in those cases? I'm not exactly sure. So I'm running this little code to make an intersection over union, and what you're seeing here is just the output. It's going label by label for the validation data set and saying how good it is with IOU. That's what this number is here. So a perfect IOU is 1. That means the intersection and the union are the same thing. That means we have a perfect bounding box compared to our validation data set. A really bad one would be 0 or just nothing. So yeah, I guess we didn't do terrible. Yeah, so that's one way to assess accuracy with these bounding box detection models. We can try to visualize it. So if I click this, I think it will actually make a few examples of comparing a truth box with a predicted box. Let's see, is it in here? How did that go? Oh, okay. All right, that should help. So I believe which one is which? I think the predicted box is the thick one, and the truth might be the thin one. No, it's the opposite. Yeah, it's the opposite. So the thick box is what I labeled myself. So that's ground truth of what a tree is. And then the thin box is what it was predicted. And so you can see there's not perfect alignment, there's overlap. And so then you can use the intersection over union to see how good that is. And then like here's one where I predicted that this was a tree and there's obviously no tree there. So what does that get quantified as? I don't know. I guess you just call it 0 or NA, or I don't know. I'm sure you could handle that in a number of different ways. Here's another one. The thick box is what I said is the truth. That's a little tree, but it was predicted a little offset of that. So we didn't have a perfect prediction. We were close. We're not quite perfect. Okay, so that's doing some accuracy assessment. And there's a lot more, and you can dig way deeper into that. This is just the very surface, one way you could look at accuracy. These other boxes here show you different ways to look at the results. We'll just go past them and get to something else. But yeah, keep in mind, with all the steps we've done today, I'm just scratching the surface to get you a basic workflow of how this goes. But of course, every little step is infinitely deeper. Machine learning is a deep field, and there's a lot to it. Okay, what else would you need to do? This code snippets will save the model and load a fine-tuned model. So we can actually take our new fine-tuned model, click this, and I believe it should have created an output of it. So content fine-tuned model. Yeah, here it is. So golf course deep forest .pt. That is the model that we created with the training data. It exists as a file, right? It's got bits and bytes and ones and zeros, and it's a thing. It's a file that can be moved around or shared or downloaded or anything you want. So that is Deep Forest plus my little golf course labels. I've created Jeff's detector. Maybe I should have labeled it that, Jeff's detector. And so yeah, that can live on. So then you could hand it over to your friend, and your friend could add more labels to it to train even more. So it becomes this thing that can live on, and yeah, it's like a building block. It's like a Lego. Here's some code for bringing an existing model into Colab. We already did this at the beginning of the session. What else? Here, we can directly, with this code, we can directly upload a model that we created here directly into Hugging Face. And this would only work if you have a Hugging Face account and you've already got the API key for that to work. So it's just kind of a shortcut, I guess, to take a model that I created here in Colab and then save it someplace. You can save that down your local machine, or you can just push it directly up to Hugging Face. And I wonder if I can do that here. All right, so I had to install Hugging Face Hub Python library. Okay. For me to do this, I need to go to Hugging Face. What do we got in the chat? What you got there? Thank you, Carlos, to save Deep Forest train model. Okay, is that just another way to do it? Okay, in the interest of time, I won't actually log into Hugging Face, but this is Hugging Face. This is the website where you can upload data, download data, post your machine learning model, find pre-baked, pre-trained machine learning models. Is kind of just a great hub for doing machine learning. Actually, I do have it. I will not do it because I don't want to show you guys my API key. But I think you got the idea. I can run this code and I can just push my new model directly up to a repository on my Hugging Face account. And then I can make that available to anyone in the world through a download. Yeah, exactly. Stephanie here in house said, how do you know what to trust? What's a good model? I don't think there's any, great thing I could say about that other than how many other people have downloaded it, right? That's one method. How much attention has it gotten, or do you know the people? Or
it's really bad. Get a lot of attention just for the fact that
perhaps, that I guess you could say something about anything online. How do I know this thing online is any good? Well, I don't know. Either you just try it or you have somehow heard about it. Some of your colleagues mentioned it, or maybe you see it on there and you're like, wow, it's got 10,000 downloads, maybe, you know, that's usually an indicator of something that it's popular.
That oh, here is mine.
Exactly. Yeah. So this is where word of mouth, you know, becomes a thing. And then social networks like LinkedIn or, you know, any social network you could imagine. Yeah, that's kind of how you find stuff.
Like QGIS plugins actually have like a rating system,
Oh, nice.
so you
Nice.
can see like, you know,
So-
how many reviews they've gotten.
Okay. I wonder if there's something like that in Hugging Face, some kind of like, yeah, 4 stars or something. I'm not sure, but I assume there's some kind of way to look at something like, oh yeah, that must be a good one. Yeah, I think that's pretty much it. I think we're able to get through the whole notebook. Okay, so let's just kind of re-summarize what we did through this whole workflow. What did we do? We found a pre-trained model on Hugging Face. We did zero-shot prediction. It wasn't that great, so then we went into Label Studio, made our own labels of trees in the golf course, brought those labels into Colab. We did our own fine-tuned training. We reran the prediction, and then it looked like it was better, at least visually. And then we did a little bit of accuracy assessment using intersection over union. And then, you know, around and around we go. Usually you're going to go through this machine learning workflow many times, many iterations to get to a model that works for you, whatever your area of interest is, whatever you're trying to identify in imagery. What I'm excited about going forward is the possibility of this whole workflow being automated with AI agents. And that seems like that is just about possible. Um, Carlos, have you used LangChain to do something like this? Okay, well, so the machine learning industry is getting more and more sophisticated every day. There's millions of people that are in it, and it's just getting more and more and more automated. I showed you a very basic workflow, but if you get in with people that have been doing this for years, they're going to show you all kinds of shortcuts. Yeah, and imminently, a lot of this is going to be automatable. I think the labels, you know, actually drawing a box around the tree of interest is still going to be kind of a manual process, but all the rest of it could just be automated with AI agents. And I assume that's happening already with people that are deep into this, and hopefully becomes easier to people like me that are not a super deep machine learning engineer. So yeah, with more automation, that means this will become easier. We'll be able to make more sophisticated machine learning models quicker for all kinds of purposes. So it is really exciting to kind of get into this field and see how the automation takes off with AI agents. Okay, we're at 11:26. For those who stuck around, I really appreciate it. And that's about it, guys. Is there any questions about the workflow, what we did? Did I miss anything? I know I kept it pretty shallow, you know, just trying to get through the workflow without going too deep into any one part.